Hello everyone. In this video, I will show you how to use deep learning for football analysis based on game recordings. So the main idea is to extract useful information from video recordings of football games. And more precisely, the ultimate goal is to track each object of interest, such as the players and the ball, and to capture the coordinates of each tracked object at any given frame with relatively high accuracy. And this would certainly allow us to calculate many useful statistics, such as ball possession rate, players' traveled distances, the ball and players' average speed, and many other statistics. However, as you can imagine, there are many challenges that we need to overcome in order to achieve that goal. So the application we have today presents the first step, and its main functionality is to detect the players, the referee, and the ball, then seamlessly project their coordinates on a tactical map representation of the football field. Okay, so now let's start with a demo for the web application, and then I'll be explaining the different functionalities and the reasoning behind their implementation, and finally we'll do a simple code walkthrough. And of course you can find the different files for this project in the GitHub repository, which you can access through the link in the description. One last thing I need to add before we start the demo is that when training the object detection models, I used the tactical recordings of football games. And that's because if we want to achieve a highly accurate tactical map representation, we need either a fixed camera or a camera that doesn't move too much. And that's why I decided not to use the regular TV broadcast recordings of football games. Okay, so without further ado, let's start with the web application demo. Okay, so here we have the web app for football players detection with team prediction and tactical map representation. So the first page here is a how to use page. You can follow the different steps here in order to navigate the app and learn how to use it. But I'll show you how in this quick demo. So first of all, we start with the main settings. We need to select a demo video. We have two options here. And here we have the first one selected. But of course, if you want to use your own video, you can upload it using this button. And then you can preview your uploaded video over here. So let me show you, this is the first demo video. It's a tactical camera recording for the game between France and Switzerland. So the next step is to set the team names. So the first team here is France and the second team is Switzerland. Then we need to move on to the team colors tab. And here we need to set the different team colors that will be used afterwards for team predictions. So here we have a select frame slider, and we need to select frame where every player is detected. For example, here in the first frame, we don't see the goalkeeper of the Switzerland national team detected. So we need to choose another frame. For example, in the second frame, we can see that both goalkeepers of the two teams are detected, and we can work with this frame. And then we need to select the different colors for both teams. So for each team, we have two colors, one for the players and one for the goalkeeper. And to select the colors, we simply need to click on which color we need to select, and then click on the detection images here. So for example, for the France player's color, we simply click, for example, on this pixel, and the picked color will be shown in the box below. Now let's select the color for the France goalkeeper, and we repeat the same process. We pick a color, and it will be shown here. We can do the same thing for the Switzerland team. First the player's color, and finally the goalkeeper color. Of course, you don't need to do this for the demo videos because the different colors are predefined. But if you want to upload your own video, you need to perform this step in order to get a correct or an accurate team prediction. Once we have the different colors set, we can move on to the last tab, which is the model hyperparameters and detection. Okay, so the different parameters here will be discussed later on, but here we have annotation options, which are detection options. So if you want to show the key points detection, the player's detection, the color palettes, or the ball tracks, you can toggle these options. And you can save the output video if you check this box. And of course, you can enter the file name, which is optional. If you don't want to enter a file name, one will be generated. And you can find, of course, the output video in the output folder. Let's start with the player detection option. Alright, as you can see here, we have the different players detected. and we have the team prediction for France and Switzerland. And here we have each player with the color palette detected, which is used for the team prediction. And of course here we have the tactical map with the ball track representation. Now the FPS here is low, is around 4 on average, but if we run the same code on a Jupyter notebook, we can get it up to 8 FPS. But of course, many more optimization steps can be taken in order to improve the FPS. Alright, now let's stop the detection and add the show key point detection option. Let's start again. Now it will show you the different field key points that were detected, and these key points are used to build the tactical map representation. And as you can see here, we have an efficient and accurate key point detection. Alright, now let's move on to the second demo video. So we simply need to select the Demo 2 option on the main settings, and everything else will be changed accordingly from the team names to the team colors. So we only need to click on Start Detection. Alright, so here we have two teams with quite similar colors, and that's why the team prediction isn't as accurate. And we will discuss later on what can be done to improve on that. And if you've noticed it as well, in the beginning the tactical map representation wasn't accurate, but then it got corrected when the camera started moving. And that's another functionality implemented to correct the different representation based on the camera movement. Okay, so that's it for the demo. Let's stop the detection and let's discuss how the different functionalities were implemented. Okay, so here we have a flowchart of the football analysis web application. And we start here with an input video, of course, which is passed to two object detection models, as you can see here. So the first functionality in this web app, and the most crucial one, is the detection of the different objects of interest in the input video. And here I trained two models, one for the player, the referee, and the ball detection, and the other one is for the field key points. So the models I trained are Yolov8 models, which were trained on a custom dataset that I labeled manually. Each dataset contains about 500 images. And as I said earlier, I used tactical map recordings of football games in order to create these datasets. And I used free annotation tools, LabelMe and CVAT, for the annotation of the datasets. Now I won't go into details on how to install and use these tools, but you can find different guides on the internet and in their respective GitHub repositories, which you can find the links for in the description. So now that we have the datasets, we can train the YOLO models, and I've used a hyperparameter tuning technique implemented in Yolov8 to achieve great results even with these small custom datasets that I've created. So as we can see here, the confusion matrices shows that we have achieved relatively great results for all the different classes in both models, except for the ball class, where it only predicted 25% of the balls present in the validation set. So we have low recall for the ball class, and that's expected, of course, because the ball class was underrepresented in the dataset, which is also true for other field key points. And as we've seen, that class imbalance affects especially the recall for those classes, meaning that the object won't be detected as much as we want to. And this issue can be addressed using larger datasets or through data augmentation techniques. But for the time being, I'm satisfied with the current model's results. But if you want to train a more accurate Yolov8 model, it is recommended that you use at least 1500 images per class. And you can find the different tips on how to create a good custom dataset on the Yolov8 documentation page, and you can also find the link for that in the description. Alright, so now we have the models we need. That pretty much represents all the machine learning present in this application, and all the remaining functionalities are simple computer vision algorithms that uses the results obtained from these detection models. So the results from the player's detection model are used first to extract the color palette for each detected player. This extracted color palette will be used later on to predict the team of the detected player. And the result from the key point detection model is used to calculate a homography matrix, which is a matrix that maps the key points position on the tactical map and the position of the detected key points on the video. So once we have the homography matrix, we can map each point on the frame to a point on the tactical map. And that is indeed the next functionality, which is calculating the player's position on the tactical map. So once we have the bounding boxes for each detected player, we can get the coordinate of each player on the frame, and then using the homography matrix, we can map that coordinate to the tactical map, and that's basically how we get the representation. Now once we have the team predictions for the detected players, we can add that as well as the ball tracks representation on the tactical map in order to generate the output video. Alright, so now let's discuss a little bit further the algorithm used for the team prediction as well as the homography transformation. For the team prediction algorithm, I was first thinking about using a clustering algorithm or clustering model with two clusters, let's say for example team A and team B, and that way I thought we could distinguish both teams. So I tried this idea, and here we have, for example, for this frame we need to extract all the players' bounding boxes. After that I wanted to use the extracted images of the players to train the clustering algorithms. I tried k-means and dbscan. Well, obviously we need to train a model every single frame since we will not be tracking the players, and that's exactly why we can't be using the images as a whole for the training process of the clustering algorithm, as it will make the app very slow. But I tried multiple feature extraction methods, such as using a pre-trained CNN or averaging the colors present in each image, or extracting the dominant colors palette. These extracted features, I tried to use them for the training of the clustering model. However, no matter what feature extraction method we use, I obtained very poor results regarding the instantaneous team prediction. And to illustrate the main issues regarding this approach, let's check this example. So here we have a random frame where we have successfully detected the different players and calculated the average color for each player in this image. And here we have the position of each player in the RGB space. Now we can see clearly that we have a player far away from all the others, and that's because we detected the goalkeeper in this frame that is wearing a reddish colored kit. So using dbscan is expected to fail in this case, but even if we remove the goalkeepers from this equation, we still don't see a clear separation between both teams. That's understandable since both teams are wearing a shade of blue. So I figured let's use a rather straightforward solution without any machine learning model. And that is by defining from the start the colors of each team. And then each time we detect a player, we can extract its palette of dominant colors and then calculate the distance between those colors and the predefined team colors. And as such, we can assign each player to its team more accurately. But since we have the green grass present in almost every image of detected players, we can expect that the green color will always be present in the color palette we extract, which is not very useful for the team prediction. So that's why I decided to use a smaller centered rectangle to extract the color palette, as shown here, and that indeed improved dramatically the accuracy of the team prediction algorithm. One last thing I need to note before we move on to the next functionality algorithm is that the distances between the extracted color palette and the predefined colors are calculated in the LAB space, not the RGB space, and that's because it is reported that the distances in that space are more meaningful and are much closer to the perception of the human eye, and that's what we want. Okay, so now let's move on to the next functionality, which is transforming the coordinates of the detected players from the frame plane to the tactical map plane. Now, as I said, to achieve this transformation, we will be using something called the homography matrix, which is a commonly used matrix to shift perspective. So as illustrated in this image, we can use it to look to the same scene from different point of views, and the transformation from one POV to the other is obtained through this homography matrix. So this is exactly the transformation we need to use in this application. And to achieve that, we need to map at least 4 points from the first point of view to the second point of view. And in our case, we have a tactical map in which we defined a certain number of key points and saved their coordinates. Now, when we detect at least 4 key points on any given frame, we can calculate a homography matrix. And as you can see in this example, one thing I noticed is that with exactly 4 key points, we can have 100% accuracy of POV shift using the homography matrix or the homography transformation, especially in the proximity of these 4 points. However, when we increase the number of key points, the accuracy will decrease, and that can be due to a slight warp in the camera recording, or in case the points are not in the same 3D planner, as I found mentioned in this Stack Overflow post. And after some trials, I figured that the error from the homography transformation is not that big, so we can work with it for now. But the main issue was the shaky and jumpy behavior of the coordinates on the tactical map, which is due basically to the fact that we're calculating the homography matrix in every single frame where we detect more than 4 key points. And that's why I introduced a homography matrix update condition that is used to determine in every single frame whether to update the homography matrix or to use the last one. And this would obviously reduce the computational cost, which will improve a little bit the frame rate and also make the tactical map representation much smoother. And the condition I set is a rather simple one, where in each frame, if we detect more than a certain number of key points that were detected in the previous frame, we calculate if those common key points have moved on average beyond a certain threshold, and if that's the case, we need to update the homography matrix, and if not, we will keep using the last calculated one. So the number of the common key points, as well as the distance threshold, are hyperparameters that should be set carefully. Now once we have the coordinates of the players and the ball on the tactical map, we can easily track the ball movement, since we only have one ball present in the field at each frame, and that indeed presents the last functionality of this application. And finally, the annotated frame is displayed, and as we've seen in the demo at the beginning of this video, we have on average 4 FPS, but as we can see here, if we run the same code on a notebook, we can improve that FPS up to 8 on average. Alright, so now let's go over the code for the different functionalities that we discussed. So first, we need to get the labels as defined for the two datasets, and as we can see, we have them stored in these YAML configuration files that were used to train the Yolov8 models. So now we have both the numerical and alphabetical representation of the different labels, and we will be using that to identify the objects we detect. So then we need to set the video paths as well as the team colors parameters. And as I mentioned earlier, we convert the colors to the lab format in order to calculate the distances for the team prediction. Then we need to import the YOLO models. So we have two models for the player detection and for the key points detection. After that, we set some hyperparameters such as the confidence threshold for both models and the key point displacement threshold. And then we start the capture loop. So in this loop, we will process each frame. So here we first increment the frame counter and we read the frame from the capture. So in each frame, we create a new copy of the tactical map, so we can display the detected object's coordinates. And then here we set the ball tracking history variable in case we exceeded a certain number of frames without detecting any ball object. So the first part in this code is the object detection and coordinate transformation. So here we get the result from both models' detections, and we can see we have the results stored here for the bounding boxes for both models, as well as the labels, and then we can extract the alphabetical representation of the detected labels. After that, we need to get the detected key points or field key points coordinates on both the tactical map, which are predefined coordinates, and the coordinates on the current frame. We will be using those coordinates, of course, to calculate the homography matrix. So here, if we detected more than 3 labels, meaning 4 or more key points, we will check the update condition. And here we have the frame number bigger than 1, meaning that if we're on the first frame, we of course need to calculate the homography without checking the condition because we don't have a previously calculated homography matrix. But if the frame number is bigger than 1, we need first to check how many common key points are detected. So if we have more than 3 common key points detected, we need to calculate the error between the position of the detected key points on this frame and on the previous frame. So here we used the mean squared error, and if that error exceeds a certain predefined tolerance, we need to update the homography matrix. Now the homography matrix is calculated using this function, find homography from OpenCV. And I forgot to mention that there are other methods to calculate the homography matrix or to perform perspective shift. And there are ones that involves deep learning or machine learning, but I wanted to keep things simple for this application, and using this function from OpenCV, we can obtain relatively good results. So once we have the homography matrix, we can transform the coordinates of the detected players from the frame to the tactical map, and we can achieve that using a simple matrix multiplication as shown here. So then we need to transform the ball coordinates as well, And as a final step, we update the ball tracking history, so we save the position of the ball on both the tactical map and the frame, but we will only display the tracks on the tactical map, since the tracks on the input video are not relevant since the camera is moving, so the tracks won't be reliable. And we have here set some conditions for the track history. So for instance, this first condition would create new track for the ball if it moved dramatically from the previous position, and this condition here would prevent the ball tracking history from surpassing max length that we defined earlier. So the second part of this algorithm is the player's team prediction. So first of all, we need to convert the frame from BGR to RGB, since we're using OpenCV, and it uses as default the BGR setting. Then we have this loop which will extract the color palette from each detected player. So the first part here is to extract a centered and much smaller rectangle instead of the whole bounding box of each player. And this centered filter would be used to extract the color palette. So the color palette extraction is performed using this function from the Pillow library. And once we have the color palette extracted, we need to get the top dominant colors. So here we calculate the redundance of each color and we sort the values. Then we can get, for example, the top 3 dominant colors, which are defined in this palette interval variable from 0 to 5. Alright, so once we have the color palette, we can append it to this list. And then we can use the list of extracted color palettes to predict the team for each player. So as I said, we will be using the distance in the LAB color space. So that's why we first need to convert the detected color palettes from RGB to LAB. And then here we calculate the distance using this method from skimage, which calculates the Euclidean distance in the LAB color space. So in this loop, for each color in each color palette, we calculate its distance from the 4 predefined colors, and then we can assign each color to the corresponding team, which is closer to that color. So here, for instance, we have a palette of 5 colors, and each color will be assigned a team. And then using a simple voting mechanism, we can get the team prediction for each player, which is performed in this loop. So we loop over the different player distances, and then we predict the player's team by vote counting. And that's how we perform the team player's prediction. And now moving on to the last part, which is to annotate the current frame and the tactical map. So first we loop over all the detected objects by the player detection model, and we display the color palette next to each detected object bounding box. And then we annotate the tactical map with the player position for each team with the corresponding color. And then we add the annotation, of course, for the referee bounding box as well as the ball bounding box. And then we add the ball tracking line on the tactical map. And as a final step, we combine all the annotation in one single output frame. And then we display the output frame and we move on to the next iteration. Alright, so let me now run this code to show you what is the expected result. Alright, and as you can see here, we have a higher frame rate, and you can see all the different annotations that we discussed. And you can click on P to pause the detection or Q to quit the detection. Alright, so that's it for this application. As I said, you can find the code for this project in the GitHub repository through the link in the description. And that's it for this video, so see you next time.